In this video, I am going to talk about 30 AI concepts that will help you understand the basics, the terminology, and the concepts that is required for every AI interview. I'll start with basics of machine learning, since understanding machine learning is very important for any AI engineer. Then we go into generative AI, LLMs, and so on. So let's get into it. What is artificial intelligence? Let's start with the big umbrella term. Artificial intelligence is any system designed to perform tasks that would normally require human intelligence. But here's what most people get wrong. They think AI is one thing. It's a spectrum, a spam filter that follows. If email contains these words marked as spam, that is AI. A self-driving car processing millions of sensor readings per second, that's AI. ChatGPT writing you a poem about your cat, also AI. Wildly different systems, same umbrella. Number 2 is machine learning. Machine learning is the subset of AI where instead of telling the computer what to do step by step, you show it examples and let it figure out the rules on its own. Here's the difference. Traditional programming is where you are the chef. You write the recipe. If temperature is above 30, turn on the AC. If below 15, turn on the heating. Every rule, you are writing it. The computer just follows the instructions. In machine learning, you don't write the recipe. You show the computer 1,000 meals and say, figure out how to cook it. You give it inputs and the correct outputs, and it works backwards to learn the rules connecting them. That's the mental model shift that changes everything. In traditional programming, humans write rules. In machine learning, data and model writes its rules. Number 3, supervised learning. There are 3 main paradigms of machine learning. And in that, supervised learning is when you train a model on labeled data where every input has a known correct output. Imagine you are teaching a kid to recognize animals. You show them a picture of a cat and say that's a cat. Picture of a dog and say that's a dog. You do this thousands of times and eventually the kid can look at a photo they have never seen and go, that's a cat. That's supervised learning. Examples are regression and classification. Number 4 is unsupervised learning. Unsupervised learning is when you train a model on unlabeled data and let it discover hidden patterns or structure. It's like you dump the full messy unlabeled data and you don't tell the model anything, and the model comes back to you with answers and patterns that it understands. Examples are clustering. Number 5 is reinforcement learning. Reinforcement learning is when an agent learns by taking actions in an environment and receiving rewards or penalties to maximize a long-term goal. Think of how you learn to ride a bike. Nobody handed you a textbook. You just got on, wobbled, fell off, adjusted under balance, tried again. Every time you stayed upright a bit longer, that's the reward. Every time you fell, that's the penalty. Eventually you figure out how to balance without even thinking about it. That's reinforcement learning. Examples are AlphaGo, and even ChatGPT used RL to make it useful to us. Number 6 is exploratory data analysis, is the process of examining and visualizing your data set to understand its structure, patterns, and problems before you even build any model. Think of it like being a detective at a crime scene. You don't start making arrests the moment you arrive. You walk around, look at the evidence, check what's missing, spot what doesn't belong, and build a picture of what happened. That's EDA for you. In practice, this means asking questions like, how many rows and columns do I have? Are there any missing values? And how many? What do the distributions look like? Are they skewed? Or are there any outliers? Are there any features correlated with each other? Does the target variable have a class imbalance? Number 7 is data preprocessing. Data you have in real world is often messy and you need to treat it before you feed it into the model. Think of this as before you cook the meal, you need to wash the ingredients, and that is data processing. In data processing, you primarily handle missing values. You ask yourself, do you fill them in or do you drop it? Remove duplicates, normalizing numerical features so they are on same scale. You don't want salary in thousands sitting next to age in tens, because the model will think salary matters more just because the numbers are bigger. Coding categorical variables, turning red, blue or words into numbers, the model can actually work with it. If you skip this step, your model is learning from garbage, and garbage in, garbage out. Number 8 is feature engineering. Feature engineering is the art of taking your raw data and creating new variables that help the model see patterns it wouldn't have found on its own. Say you have a timestamp for every transaction. So for example, 14 March 2025 means nothing to a model, but extract day of the week, hour of the day, is it a weekend? Is it a public holiday? Suddenly, the model can spot that fraud spikes at 3 a.m. on weekdays. You give it the same data, you just presented it in a way the model can use. A good feature can be worth more than a better algorithm. In interviews, talking about feature engineering before jumping to model selection shows you actually worked in real time. Number 9 is which model for which task. Before you learn the fancy architectures, you need a mental map of which model goes where. Think of it like it's in a toolbox. You wouldn't use a screwdriver to hammer a nail. Small data, simple problems, start with basics. Logistic regression for classification, say you are a bank and you want to predict whether a loan applicant will default or not. You've got a spreadsheet with their income, credit score and employment history. Logistic regression takes those inputs and gives you a yes or no answer. Say you are an real estate agent and you want to estimate a house price based on square footage, number of bedrooms and postcode. Linear regression draws a line through your data and gives you a number. Nothing fancy, but linear regression does the job. A simple model with good features will beat a complex model with bad data every single time. Which models for task? Number 2. You have got your baseline results and want to improve your model's performance on tabular data. Then this is where 3 models dominate: XGBoost, LightGBM, CatBoost and Random Forest. These are fast, these handle messy data very well, and they consistently win on structured data. If you have image data, then CNNs, convolutional neural networks, are built for this. They are built to detect visual patterns like edges, shapes and textures. If you have text data and want to build models for language understanding, then summarization, translation, transformers, BERT is way to go. This is the base architecture for many large language models today. So how do these models learn anything? Like any task we do, where we start off terrible and learn based on our mistakes and improve, that's how a ML model learns as well. Every model starts off terrible. It makes random predictions and gets almost everything wrong. So how does it go from terrible to being useful? 2 things, a loss function and a gradient descent. First, the loss function. This is how the model knows it's wrong. It compares what the model predicted versus what the answer actually was and spits out a number. The bigger the number, the worse the prediction. For regression, you will see mean squared error. For classification, you will see cross entropy. Different formulas, but they have the same idea, a score that says how far off you are. Now, the model knows how wrong it is, but knowing you're wrong doesn't fix anything. You need a way to get better. That's gradient descent. The model needs to update its weights to get better. After every prediction, the model asks which weights made me wrong and which direction should I adjust them. It figures out using something called backpropagation, which traces backwards, calculating exactly how much each weight contributed to the error. Then every weight gets nudged slightly in the direction that reduces the loss. Number 12, train, validation and test split. The train, validation, test split is how you divide your data to ensure your model actually generalizes to data it has never seen before. Here's the golden rule. You never evaluate a model on the same data you trained it on. Never ever. Split your data into 3 parts. Training set, the model learns from this. This is its classroom. Validation set, you use this during training to tune your settings and check if the model is overfitting. Think of it as your practice exams. And test set is you touch this once right at the very end for a final unbiased grade. This is the real exam. A common split is 70-30 if you have no validation set, or else 80-10 would suffice. Number 13, overfitting is when your model memorizes the training data instead of learning the actual patterns. So it performs great on training data, but terribly on anything new. Think of that student who memorizes every past exam paper word for word. Ask them the exact same question, perfect score. Change one number in the question, they are lost. That's overfitting. The model hasn't learned the subject, it has just learned the answers. In interviews, if someone tells you the model has high training accuracy but low test accuracy, the answer is always overfitting every single time. Number 14, underfitting. It is the opposite of overfitting. Your model is too simple to capture the patterns in the data. It performs poorly on everything, training data included. Underfitting is like that student who skimmed the textbook the night before the exam and only learned the chapter titles. They can't answer anything in detail because they never went deep enough. The entire game of ML engineering is finding the sweet spot between these two. Too complex, you overfit. Too simple, you underfit. Techniques to fight overfitting are regularization, dropout, early stopping, data augmentation, and for underfitting, it is simply getting more data. Number 15, model evaluation metrics are the measurement you use to decide if your model is actually good enough to ship. Let's start with accuracy and why it's a trap. Say you are building a fraud detection model. 99% of transactions are legitimate, 1% are fraud. If your model just predicts not fraud every single time, it gets 99% accuracy. It sounds amazing, but it catches no fraud. Completely useless. So instead, you use 3 metrics. Precision. If everything the model flagged as fraud, how many were actually fraud? High precision means fewer false alarms. Recall. Of all the actual fraud cases, how many did the model actually catch? High recall means fewer missed cases. F1 score is the balance between precision and recall. One number that tells you how well the model is doing on both. For regression problems, predicting a number like house price or temperature, you use mean absolute error, mean squared error, or R squared. Here's the interview question that always comes up. When would you optimize for precision over recall? And the answer is, it depends on what kind of mistake is more expensive. If you are building a cancer screening tool, then optimize for recall. You would rather flag a healthy person for a second test than miss someone who is actually sick. If you are building a spam filter, optimize precision. You would rather let a spam email through than send your boss's email to junk folder. Number 16, neural networks. A neural network is a system of layered nodes inspired by the brain. It has neurons that learns patterns by adjusting the strength of connections between those nodes during training phase. Think of it like a factory assembly line. Raw materials come in one end, that's your input layer. Each station along the line does something small to the material, inspects it, shapes it, filters it. Those are your hidden layers. And at the end, you get a finished product, that's your output. Each connection has a weight. During training, the network adjusts these weights to get better at the task. A single neuron takes inputs, multiplies each by a weight, adds a bias, and passes the result through something called as an activation function. ReLU is one of the common activation functions. Without these, the non-linear activation functions, the entire network would just be one big linear equation and could not learn complex patterns. Number 17, transformers. This is the architecture that changed everything. The transformer is foundation of GPT, BERT, Claude, and basically every major language model that you use. Before transformers, RNNs process words one at a time, left to right, like reading a sentence through a keyhole. By the time you reach the end, you have half forgotten the beginning. Transformers solve that completely. Instead of reading one word at a time, they look at the entire input at once through something called as self-attention. Take the sentence, the cat sat on the mat because it was tired. What does it refer to? The cat. You know that instantly, but a model reading word by word struggles because cat and it are far apart. Self-attention solves this. It lets every word look at every other word and figure out which ones are related, regardless of distance. Transformers process everything in parallel instead of one word at a time. They are dramatically faster to train than RNNs. Number 18. Tokenization. Before any text enters a transformer, it breaks down into tokens. A token isn't always a word. It can be a subword, a character, or even a byte. Modern models use subword tokenization methods like byte pair encoding. The word unhappiness might be broken down into 3 tokens. Rare words get split into many more pieces. Now, why should you care about tokenization? 3 reasons for that. Context windows. When someone says GPT has a 128K context window, that's 100,000 tokens, not words. In English, that's roughly 96,000 words. But in Hindi or Japanese, the same text takes up way more tokens because those languages get split into smaller pieces. Same window, but less space. Number 19. Embeddings. Tokens are discrete symbols, but models work with numbers. Embeddings are the bridge. They represent words, sentences, or images as a high-dimensional vector. Similar things end up close together. The embedding for king is near to queen. A photo of a golden retriever clusters near other dog photos. It gets encoded as geometry. Embeddings are foundational to modern AI. They power semantic search, recommendation systems, clustering, and RAG. Number 20. Large language models. LLMs are transformer-based models trained on massive text datasets. GPT, Claude, Llama, Gemini, all LLMs. What makes them large is billions of parameters trained on trillions of tokens. The core mechanism is simple. Predict the next token. But at sufficient scale, this produces something that can reason, write, code, translate languages, and explain quantum physics. The 2 main architectures, decoder-only models like GPT generate text left to right. Encoder models like BERT understand text bidirectionally and are great for classification and search. Number 21 is pre-training. If you know the full form of GPT in ChatGPT, it is generative pre-trained transformer. So why is it called pre-training? And what is pre-training? Pre-training is the first phase of building a language model. You take a massive transformer and feed it in an enormous amount of text, books, websites, Wikipedia, code, research papers, and give it one job: predict the next word over and over, trillions of times. Through billions of these predictions, the model doesn't just learn the language, it picks up facts, grammar, reasoning, patterns, coding logic, even common sense, all as a side effect of trying to guess the next word. The pre-training is there because of what comes after it. There is a post-training part as well to make it usable. That's why it is called pre-training. Number 22, RLHF and post-training. I've got a pre-trained model that can predict the next word. But if you talk to it right now, it's weird. It rambles, it says things it shouldn't. It doesn't feel like a conversation. So how does the actual pre-trained model go from a model to something which is usable like ChatGPT? The answer is post-training, and the most important technique in post-training is called RLHF, reinforcement learning from human feedback. So it has 3 steps. Step 1 is supervised fine-tuning. You hire humans to write ideal responses to thousands of prompts. If a user asks this, the perfect response looks like this. Train the model on those examples so it gets the general idea of how to be helpful. Step 2, build a reward model. You show the model a prompt and have it generate several different responses. Then humans rank those responses from best to worst. You train a separate model, the reward model, to predict those human rankings. Now you have an automated judge that can score any response without needing a human every time. Step 3, reinforcement learning. You let the LLM generate responses, the reward model scores them, and the LLM gets updated to produce responses that score higher. Over thousands of iterations, the model learns to be helpful, harmless, and honest. Number 23 is prompt engineering is the skill of crafting inputs to get better outputs. Key techniques are zero shot, which is just as directly summarize this article. No example, no setup. Works for simple tasks. Then few shot. You have the model a couple of examples. The model picks up the pattern. Chain of thought. You tell the model to think step by step before answering. It sounds too simple, but it dramatically improves accuracy on maths, logic, and complex reasoning. More advanced prompt engineering methods are React, where prompting alternates between thinking and taking actions, and tree of thought. It explores multiple reasoning paths before picking the best one. So prompt engineering is about clarity. The more precisely you say what you want, the better the output is. Number 24. RAG stands for Retrieval Augmented Generation. And here's the problem RAG solves. LLMs have a knowledge cutoff. They only know what was in their training data. Ask it about your company's internal policy or documents or last week's earning report, and it will either make something up or say I don't know. That's not useful. RAG fixes this by giving the model fresh, relevant information at the moment it sees and needs it. Here's how it works step by step. A user asks a question. You take that question and convert it into embedding. You search a vector database for documents that are most similar to that question. You take those documents and stuff them into prompt alongside the question. The LLM reads the documents and generates an answer based on what it just read, not what it memorized months ago. It reduces hallucination because answers are grounded in real documents. It stays up to date without retraining, and it gives you citations. You can point to exactly where the answer came from. Number 25. Vector databases. A normal SQL database works on exact match. You ask for customer ID 5427 and it finds exactly that row. But what if you want to search by meaning? You type how do I reset my password and you want it to find a document titled account recovery steps. Even though those words are completely different, a normal database cannot do that. And that's why we need a vector database. It stores embeddings and it finds the ones closest to your query, not by matching keywords, but by matching meaning. Cosine similarity is the most common method to find the similarity between two words. It measures the angle between two vectors. The smaller the angle, the more similar the meaning. Some of the vector DBs out there are Pinecone, Chroma, and many more. Number 26. AI agents. Everything we have covered so far, the model just responds. You ask it, it answers. An agent is different. It doesn't just respond to things, it does things for you. Here's the difference. You tell a chatbot, book me a flight to Dubai for next Friday. It says options that are helpful, but you still have to go book it yourself. An agent would actually check your calendar, search flights, compare prices, pick the best one and book it. The pattern behind every agent is very simple. Think, what do I need to do next? Act. Use a tool to do it. Observe. Check what happened. Repeat until the job is done. The tools an agent can use are whatever you give it. A calculator, a web browser, a database, a code interpreter, an email client. The model decides which tool to use and when to use it, and what to do with the result. Frameworks like LangGraph, Crew AI, AutoGen, Browser Use, these are good frameworks that you can build your agents. Number 27. Hallucinations. Hallucination is when a language model makes something up and presents it as a fact, and it does it with complete confidence. Ask an LLM what paper has Professor Smith from Oxford published, and it might give you a list of five papers with titles, journals, and dates. Sounds perfect. Except 3 of those papers don't exist at all. The model didn't look them up. It generated what plausible sounding papers would look like. This happens because model isn't a database. It doesn't retrieve facts. It predicts what text is most likely to come next based on patterns it learned during training. Most of the time that produces accurate information, but sometimes the most probable next word isn't the true next word. So how do you fight it? RAG is one way. Guardrails, checking outputs before they reach users, and confidence calibration, training models to say I'm not sure when they actually aren't. And the big one is building robust evaluation pipelines. Number 28. LLM evaluation. Evaluating a traditional ML model is straightforward. Precision, recall, F1, and then you're done. Mostly done. Evaluating an LLM is a different ball game. How do you score an open-ended text response? There is no single right answer. For example, explain quantum computing could have 1,000 valid responses. So how do you measure one is better than another? You break down into simple dimensions. Faithfulness, if the model was given context documents, did it actually stick to them or did it make up things? Relevance, did it answer the question that was asked or did it go off on a different tangent? Correctness, are the facts right? Coherence, does the response actually make sense? Toxicity, is there anything harmful in the output? Tools in the space are Ragas for evaluating RAG pipelines end-to-end, Langsmith for tracing every step of your LLM application and spotting where things break. So for most production systems, you'll end up building custom evaluations specific to your use case. A legal AI needs different evaluation criteria than a cooking assistant. Number 29. MLOps and LLMOps. You have trained a model, it works in your notebook. Congratulations, but MLOps is everything that happens between my model works in my laptop to my model is serving 10,000 reliable users at 2 a.m. on Sunday. And for LLM applications, this has evolved into LLMOps. Same principles, but different stack. It involves experiment tracking, where you are going to try dozens of combinations, different hyperparameters, different features, different architectures. If you are not logging every run, you'll forget what worked. Tools like MLflow and weights and biases handle this well. Model versioning. You'll retrain as new data comes in. You need to know which version is live. Roll back if something breaks and trace exactly what data and code produced each version. CI/CD for automated testing and deployment. New data arrives, model retrains, evaluation runs, and deploys it if it passes. No manual steps. Model monitoring. Your model performs great on day one, but real world data changes. Customer behavior shifts, language evolves, market conditions move. That's called data drift. If you are not watching performance in production, your model is silently getting worse and you will not know about it. Number 30. Scaling loss and emergent behavior. Let's finish with something that helps you think about where this entire field is going. Scaling laws were formalized by researchers at OpenAI, discovered something surprising for model performance. Model performance improves predictably as you increase three things: the number of parameters, the amount of training data, and the amount of compute. And it follows a clean power law. Double the compute, get a predictable improvement every time. This is why the AI race became a compute race. Companies poured billions into bigger models, bigger clusters, more data, and it kept working. A fascinating part is emergent behavior. At certain scales, models suddenly develop capabilities nobody programmed or expected. A model that can barely do basic math at 10 billion parameters suddenly becomes decent at 100 billion parameters. On top of that, chain of thought reasoning, code generation, translation between languages, it barely saw. These abilities seem to just appear at specific scale thresholds. And one of the research papers says that it's divine benevolence because there is no answer why the model performance has improved. The main aim of this video was to get familiarized with basic concepts and taxonomy. We have just scratched the surface with this video. Each of these concepts deserve a very serious deep dive if you want to be a serious AI engineer. So let's do that in coming videos. See you in the next one.